So yesterday we stopped at the point of the antiviruses process. Let me recall that again. This is my first version of antiviruses. So this is a difficult word, so let me write again. The conclusion was that PGL2N, subset of PGL2Z, this is a group and this is a monoid, and this monoid encodes all finite comparison antiviruses processes. By finite means that the compared magnitudes are commensurable. So if they are commensurable, then the process is finite. And we can also consider infinite antiviruses processes. So each finite process is something like t to the power n0 u, t to the power n1 u, etc., t to the power nk. So this encodes the ratio n0 over n1 nk. And generalizing from this, we can say that the boundary of PGLN, by which I roughly mean and the set of words of infinite length in some presentation in terms of some generators. So here my generators are T and U. So the set of all infinite words in T, U. Of course, by infinite, I mean reduced. If you write infinite many U's, that doesn't make sense because U square equals U. So infinite words of this kind, T to the power n0 U, T to the power n1 U, and this encodes the ratio n0 plus 1 over n1, etc. So here, the set of finite comparison antiviruses processes gives me the set of positive rationals, and if I do the same again for infinite processes, that is those processes which do not terminate, corresponding to non-commensurable magnitudes, the corresponding set is the set of positive real numbers. So what I intend to show here is that in quite simple terms, if you do the same thing in terms of the modular group, PSL2Z, using the standard generators that I described as S and L, then the boundary of this, that is the set of all infinite words in S and L, corresponds in a very natural way to the set of all real numbers, including positive, negative, and 0. And why am I doing this? In order to stress that this group is really simplest and most important among the 4 groups that I described. Now, how shall I do that? Consider the following process. So in the initial process, I had 2 magnitudes, A, let's say, and B. And at each step, I compared these 2 magnitudes. This was, for example, here in this case, I wrote A equals 2 times B plus some remainder, which was C. And then I compared B equals, I don't know, 1 times C plus D, and so on. The process continued in this manner. But alternatively, we can do the following thing. Instead of choosing the smallest multiple, I mean greatest multiple of B, which is smaller than A, I can choose the least multiple of B, which is smaller than A. In this case, I'm going to obtain, if I apply this procedure here, I'm going to obtain 3B, this times minus C, where this is my magnitude C this time. Yeah, this is C. And then I can continue this procedure if I call this N0B minus C, if I call this N1B, N1C times D, etc. Then I can reconstruct the ratio of A over B as the number N0 minus 1 over N1 minus N2, etc. And this is what is called a negative continued fraction. So this thing is called a regular or simple and this thing is called a negative continued fraction. Now, this infinite word can be described as a sequence of these operators. I mean, the operations that I described here can be written this times t to the power n0 and then s instead of. Recall that. Let me recall the names of my operators. U was 1 over x, s minus 1 over x, and then L is 1 minus 1 over x, T equals Ls, which is 1 plus x. So this time, this corresponds to a sequence t to the power n0 s, t to the power n1 s, etc., t to the power nk. However, there is some restriction because if I apply this to such magnitudes, this number nk can be at least 2, right? If you apply the procedure this way, these numbers n1, n2, etc., must be at least 2. Just 1 is not enough. I have to pick 2 in order to obtain some remainder. So nk is at least 2, but n0 is allowed to be 1, I guess, yeah. N0. So why this didn't give me a sequence in PSL2? Because U belongs to PGL2, but not to PSL2. So this belongs to PGL2 minus PSL2. However, S belongs to PSL2, and this also belongs to PSL2. This also belongs to PSL2. So both of the operators T and S belongs to PSL2, and these form a submonoid of PSL2 PSL2n, which parameterize positive rational numbers. If I do the same thing for infinite continued fractions, infinite negative continued fractions, I'm going to obtain similarly the set of all positive numbers. So I am close to my claim that this is really this, but in order to establish this, I need to do some a little bit more work. However, because this is an interesting point, I would like to talk about the antiphyresis process a little bit more. So this is, I mean, this is the historical antiviruses process, which is found in the book of Eudoxus, as Athanas Wardenby. However, these are quite new. I mean, people, as far as I know, started considering such things during the last century. And there's another way of applying this procedure, which is as follows. At each step, so I have my A, I have my B. At each step of the process, I can choose the one which is closest to A. Okay, so here I have 2B, and here I have 3B. Here it is seen that 2B is closer to A than 3B. So I choose 2B, and I write A equals 2 times B plus C. And then in the next step, it can be that if C is something like this, 2C, well, so this is C. 2C is closer to B than just C. So in this case, I'm going to write B equals 2C minus some remainder. So each sign here, plus and minus, depends on the number, which is a ratio of these two numbers. Let us denote this ratio by R. So rho, in this case, will be written as a number n0 plus epsilon 0 over n1 plus epsilon 1 over n2 plus epsilon 2 over etc., where epsilon I belongs to, well, epsilon is a function of the ratio, and it belongs to the set plus 1, minus 1. This process also describes some infinite word in PGL2n, so which we can write as t to the power n0 x, t to the power n1 x, etc., x1, x2, where xi is u if epsilon I is plus 1, and s if epsilon I is minus 1. So in particular, I find it a quite interesting fact of life that these numbers, epsilon 0, epsilon 1, epsilon 2, etc., are numbers which depend on the ratio rho. So what does these numbers say about the ratio rho? I think that is an interesting question, and it's worth thinking about it a little. But I don't have a precise answer to that question. So what else? In fact, by going further in this direction, you may describe, you may invent your own continued fraction, your own antiphyresis process. It is possible to do that, just more general. So this is first antiphyresis process. This is the second version of the antiphyresis process. This is the third version of the antiphyresis process. So this thing happens in PGL2n. And fourth version, this can be your version. Just pick some functions. Of course, an infinite set of functions, epsilon k, which depends on rho, each from r positive to plus minus 1. And then at each step, you choose to take whether this part or this part, depending on number epsilon. If it is positive, then I stay here. And if it is negative, I go one step further and I stop here and apply the process in this way. So if everybody understood this, I would like to give this as an exercise. Invent your own, these are called semi-regular continued fraction. For example, one way of doing this is to fix just fix some constant sequence, for example, plus, minus, plus, minus, plus, minus, plus, minus, etc. And at each step, you choose whether to take the least, the greatest multiple of b less than a, or the least multiple of b, excuse me, the greatest multiple of b less than a, or the least multiple of b greater than a, depending on this plus and minus. If it is plus, you pick this one, and if it is minus, excuse me, if it is plus, you pick this one, and if it is minus, you pick this one. This will give you some continued fraction expansion, which will always be of this form. n0 plus 1 over n1 minus 1 over n2 minus plus 1 over n3 minus 1 over, etc. But this is very simplistic as an idea. For any sequence of plus and minuses, you can do this, and it will not be, perhaps not be very interesting. But the interesting thing is to pick these numbers, plus, minus, etc., which depends on the ratio rho. For example, here, these constants depends on the ratio rho. They are not constant, but epsilon 0 and epsilon 1, etc., depend on rho. So this is your little exercise. Invent your own semi-regular continued fraction. And so, in fact, one can add one more toy to this story. In the antiphyresis process, we can just do two things. Either compare, decide which one is greater than the other, and shift their places, or if one is greater than the other, remove some multiples of the smaller from the greater. Okay, that is the idea. But let us apply another rule to this game. This time I am allowed to take multiples. New rule. At each step, multiply the ratio by some. It can be fixed or not fixed number p. By this, I mean you do it in such a way that to compare, for example, you take p to be 2. At each process, you take a, you multiply it by 2, and then compare with p. And go on this manner. And this idea will lead to a continued fraction of this form. P over n1 over p over n2 over p over, etc. Here, p is not necessarily a rational number, nor it needs to be fixed. So we can take other numbers, different numbers here, more generally. Sorry? P is any number. If you do this idea, then these continued fractions will parameterize. They will not always converge in the real topology. However, when they don't converge in the real topology, they will sometimes most of the time converge in the p-adic topology. And these processes, these parameterize the ratios which are in R, positive, and Q, p-adic numbers. So at this point, perhaps I am doing a kind of history of mathematics, and it is an integer. Because I don't, well, I started with some simple tools. So that P means that at each step I can multiply A with P. So this is a quite simple process. I can take several copies of this and then add one to the other. However, if P is an arbitrary real number, I don't know how to do it in some simple way. So what I'm trying to say is that the idea, which is as modern as a p-adic number, can be almost immediately derived from that fundamental and basic notion of antiphyresis process. So perhaps old ancient Greeks were not so far away from the notion of a p-adic number. So I would like to continue doing history of mathematics, because this is where the modular group comes from. So these numbers here, these elements are not in PGL2 anymore. The corresponding operator is T, IP, T to the power N0, IP, T to the power N1, IP, etc., where IP is the operator P over X. So these will be, in general, not in PGL2N, but PGL2Q. And we can say that these numbers are in the boundary of the group PGL2Q. So, where is X? So IP is the operator sending X to P over X. If we do a little bit more history, we must go back and question our initial setting. So we had two magnitudes. So I call them magnitudes, which were two sticks. However, you cannot apply this procedure to arbitrary magnitudes. For example, if I have a stick here, and if I have a square here, these magnitudes are not comparable. I cannot apply the comparison process because I cannot say which one is greater than the other. So somehow I must assume that in order to apply this antiphyresis process, I must assume that these magnitudes are of the same kind. So this is, I mean, we need some axioms to apply this process. So these, and the first axiom would be that these magnitudes must be of the same kind, whatever that means. Well, that means that they are comparable. One can decide if one is greater than the other. And another axiom is that it must be possible to subtract one from the other. Subtract one from the other. it is not always possible, because if I have a square like this and some region like this, perhaps they are comparable. Perhaps you can, with some work, some tidy work, you can determine if one is greater than the other. However, you cannot easily and immediately subtract one from the other. In fact, there is a theorem which says that if they have the same area, then they are co-decomposable, so one can perhaps play with this. But anyway, they are not immediately, even though they may be comparable, they are not immediately subtractable from each other. If we, however, if we take, for example, two rectangles, if you consider two rectangles, then I can do the following thing. I can do what I did here. I can take a multiple of one of the rectangles. For example, these two are perhaps not comparable, but I can take some copies of this, add them side to side until this fits into the picture, and then I can subtract one from the other. Unfortunately, when I subtract, I don't get a rectangle anymore, but two rectangles. So this is one rectangle obtained after the subtraction, and this is the second rectangle. So let me call this, if this was A and this was B, this is 4 times A, and this would be C, and this would be D. If I try to apply the same idea here, I'm going to get some fraction of the form n0 plus 1 over n1 plus 1 over plus 1 over n2 plus 1 over something plus 1 over something, 1 over plus something, 1 over, etc., which is called a branch continued fraction. If, in case, our initial rectangles are comparable in some sense, for example, if they are multiples of some small square, then we immediately see that this process terminates, right, and gives us an expression for the ratio of their areas. Why, again, I'm saying this is that these are, I think, instead of perhaps just G, or let's say PSL3Z, I think that the immediate generalization of the group PSL2 in the initial idea of antiviruses is this group. So this is the first generalization to study. If you want to concentrate on the modular group or its initial philosophy, and the second thing to study is such things. Here we don't have a group anymore, but some other structure. So let me note this as a generalization of the modular group. So all this can be made more precise, but this requires a lot of things to write, and I didn't want to bore you. If you want some more details, I can send you my notes about this. Again, please.
In the case that you do that, the weird diagram.
Here.
In those cases, so long as it's polygon-like, you should be able to cut and paste and get a rectangle shape.
Yes. So that's another game. So in my game until now, it was possible to consider multiples. But here, this is about somehow decomposing these two. There is such a theorem which says that if I have two areas of two polygons of the same area, but same area, only then I can eco-decompose them. And then I can try to compare the pieces. So that is one line of speculation.
So you can transform both to a rectangle, right? Compare the rectangle.
Of the same area, yeah. That.
The same area, like, so
I mean,
if
yeah.
there are different areas, like how you compare.
Yeah, I see. Yeah, that might be one possibility. Yes.
If the area is A, you can convert it to a rectangle of length A and breadth 1.
Yes.
So convert both of these to such rectangles and then compare.
Yes. Yeah, that might be possible, but long process because although I know the theorem, I don't know how effective it is.
So in terms of how many steps you can do.
Yes. I mean, these things are also interesting from the arithmetic point of view. For example, well, there's a theorem which says that, of theorem of Liouville, which says that x, a number x, is of the kind a plus square root of b with positive if and only if it's regular, the one that I first described, it's regular continued fraction expansion is eventually periodic. And if you play with these branched continued fractions, then which always branch into two branches at each step, then you encounter, for example, cubic irrational numbers. Not only quadratic irrational numbers, but cubic irrational numbers as well. So I think that, first of all, let me stress that this is an open question. I mean, nobody did such a thing before. How to compare two rectangles to get some branched continued fraction of this kind, and what can one do with such algebraic structures. Although it is not a research level question, I think that it is a fun question, and if you want to play with it sometime, perhaps you can discover some new interesting things. So I'm going to finish with story and turn back to my modular group and prove perhaps the most important fact about it. That is, it is a free product. So at this point, I get into contact with Olga's lectures. Because the structure of the group PSL2Z, I think it is also the starting point of her story. Am I right? I don't know. Yeah, SL2 or PSL2. So, now, miscellaneous facts. Theorem. The group PSL2Z is isomorphic to free product of where is that? So since this is an element of order 2 and this is an element of order 3, this is Z over 2Z star Z over 3Z. And I'm going to give a direct proof of this. And the proof is, not surprisingly, is a version of the Euclidean algorithm. Set S to be the matrix 0, 1, minus 1, 0. This goes to S. So this is an element of SL2Z. And this goes to S in P SL2Z. To recall, this was just 1 minus 1 over X. And let me also define the element L bar to be the element 1 minus 1, 1, 0, which goes to L. Again, this is PSL2Z, and this was 1 minus 1 over X. And here, the group is again SL2Z. So we first show that SL2 is generated by S bar and L bar. And since we have a surjection, since this is a quotient SL2Z, PSL2Z, if S and L generate this group, then PSL2 is generated by its images L and S. So I'll have shown my claim. We note that L bar, S bar is 1, 1, 0, 1, which is also called T bar, and which goes to the element 1 over X, which was T. Here on the group PSL2, and here on the group SL2. And L square bar S bar is 1, 0, 1, 1, which goes to 1 over 1 plus X, no, excuse me, X over X plus X, and it doesn't have another name, just this. And let G be the group generated by S bar and L bar. And suppose that G is not SL2Z. Now pick an element A, B, C, D in SL2Z minus G with A plus C minimum. We are going to get a contradiction from this. We first suppose that AC is not 0. Then, since L bar, S bar to the power R, X, this I call X, times A, B, C, D. This equals 1, 1, 0, 1 times A, B, C, D, which equals A plus RC. Excuse me, I should have written, but this is an R. A plus RC, B plus RD, and here I have C and D, right? Now, since X is not in G, and since G is generated by S and L, and since this element is expressed in terms of S and L, if X is not in G, then this element should not be in G neither. So this element is not in G. Because if it was in G, I could multiply this with the negative power of this to get X, to get a contradiction. Now, there are two cases. If A is greater than C in absolute value, greater than or equal to C, then one can choose an integer such that A plus RC is strictly less than A. But then absolute value of this plus absolute value of this, A plus RC plus absolute value of this, is strictly less than absolute value of A plus absolute value of C, which contradicts the minimality. Similarly, if A is greater than C in absolute value, we get a contradiction. Therefore, since in each case we get a contradiction, hence A equals 0 or C equals 0. If A equals 0, then X is of the form, of what form? 0, B, C. Here I must have plus 1, right? No. So I can have some arbitrary number. I can have some arbitrary number here, but here I must have plus 1 or minus 1, or X equals 0, plus 1, minus 1, D. X must be one of these two. But then this can be easily written in terms of L and S. In each case, X is in G, again contradiction. Similarly, if C equals 0, then we get a contradiction. Hence, there exists no such element X. Hence, SL2 Z is generated by S bar and L bar. Now, this shows that our group is generated by S and L, but it doesn't prove that it is freely generated by S and L. And to show this, we must consider the kernel, consider the kernel, which goes from Z over 2Z star Z over 3Z to PSL2 Z. Here I consider this to be the group generated by A and B, A squared equals B cubed equals 1. And this map phi sends the generator A to S here and B to L here. We know that this is a kernel of this map, which we know to be a surjective homomorphism. We want to show that the kernel of this map is trivial, and we'll have proven that this group are isomorphic, so that it's free. And to do this, let x be, then x can be written as a product of BAs, so some BAs, and then B minus 1 A's, and so on, in this form. And it can start or not with an A, and it can start or not with A, so it can finish with an A, and B plus minus 1. So x can be written in this form, but I can choose only one of these possibilities. I can eliminate the case where both are present, because then I can conjugate this with A, for example. If I conjugate with this A, then the A at the start will disappear, so that I'm going to have only BA in the beginning. So otherwise we can conjugate. So since on the other hand, SL to the power R is x plus R, and L S to the power R equals x over Rx plus 1, a product of such elements cannot contain both positive and negative terms. So these always have plus signs. So inside I cannot have a plus or negative term. And since S and L to the power plus minus 1 both contain positive and negative terms, you know, since in the image of x under phi, this would go to the unit element. If I put this to the other side, then I'll have expressed this element, for example, A, as a product of such elements. But here I only have positive entries, whereas on the left-hand side, that is A, here includes negative and positive terms, because it is written as minus 1 over x. This leads to a contradiction. Such a product cannot equal to S or L plus minus 1, which implies that X must be the identity. So I have something like 5 or 9 minutes, right? 9 minutes, okay. So from these, we derive some immediate corollaries by using the combinatorial group theory, or most of these results can also be deduced from Olga's lectures. The first corollary says that an element of finite order in PSL to Z is conjugate to L or S. Another corollary is that a subgroup of finite index of PSL to Z is of the form what Z over 2Z star Z over 2Z some M times product Z over 3Z star Z over 3Z N times product Z star Z. So any subgroup of finite index is of this form. Of course, there are also many subgroups of infinite index in this group. In fact, this group has uncountably many subgroups. So most of them are going to be of infinite index. But for the finite case, we can, and we are going to describe this in quite concrete terms. But here, let us say that any group of this form is isomorphic to some subgroup of PSL2Z. Well, if M is 1 and N and K are 0, if these two are 0, then I have only Z over 2Z. This is not a finite index subgroup. It's an infinite index subgroup. And otherwise, if this is 1 and the other are 0, this is also a finite index, an infinite index subgroup. And if this is 1 and the other are 0, this is also going to be a finite index subgroup. In the remaining cases, there are always, I can write here to some finite index subgroup of PSL2Z. In particular, it is not a consequence of this, but just some surprising fact. PSL2, I mean Z over 2Z star Z over, perhaps better, PSL2Z has a non-trivial subgroup which is isomorphic to itself. It is of infinite index. In fact, it has many such subgroups. So another curiosity, which is emitted from the description of this group as a free product, is its abelianization. Because if you abelianize the presentation, we end up with the group, so A, B. Yes.
Are they conjugate or they
They are not conjugate. There are many which are not conjugate. And if you remind me of that question sometime tomorrow or today, end of my towards the end of my talk, I can describe them explicitly. So AB equals A square, well, a square equals b, plus, and a and b commute. This is simply the group z over 2z, Cartesian product z over 3z, which is z over 6z. So the abelianization of theorem, the abelianization of PSL to Z is isomorphic to Z over, and by using Reidemeister Schreier, a simple application of that theorem is generated by what are the generators? Ls square, so Ls square, which is x plus 2, and L car S square, which is x over 2x plus 1. And it is freely generated by. So I have an exact sequence, one free group on two generators, PSL to Z, Z over 6Z, and 1. I have an exact sequence like this. So the free group on two generators is a subgroup of our group, which shows that this group is very big because any subgroup of the free group is free. So there are subgroups of arbitrary big rank inside the group PSL2Z. So in fact, it is possible to obtain presentations of the groups SL2Z and GL2Z and PGL2Z by using only elementary tools or by using the technology developed by Olga. Here I'm going to give you only a presentation for the group PGL2Z. PGL2Z is isomorphic. Well, in fact, it is the group generated by U, V, and K, and these satisfy the relations U square, V square, K square equals commutator of U and V equals KU cubed equals 1, where V sends x to minus x, U sends x to 1 over x, and K sends x to 1 minus x are three involutions. So PGL2 is generated by these three involutions, and it admits this presentation, which says that it is an amalgamated free product of the subgroups U, V, amalgamated at U of U and K, U and K. Here this group is Z over 2Z times Z over 2Z. The amalgam is just Z over 2Z, and the group generated by U and K is, I'm not sure about this. This is a symmetric group on 3 letters. This is U, so 1 over 1 is X. Yeah, I think this is the symmetric group of order 3. Is this correct? Or do you know about this something like this. And as I said, you may either play with such things to deduce the presentation or use the technology developed by Olga in his lectures to conclude immediately. Okay, this is going to be the end of my first talk. In my following talk, I'm going to talk about the fairy tree, construct a fairy tree and its boundaries.